Hi, welcome to a new lecture. Today, we'll be asking ourselves an interesting question: whether AI can discover the laws that govern a particular phenomenon provided just the data. Is this something that AI can do? So the idea is, if you just have the data set which was produced based on a certain XY functional relationship, by just looking at the data, can AI backtrack what is the function which created this data in the first place? This comes under a concept called symbolic regression within the framework of scientific machine learning. And in today's lecture, we'll be looking at this fascinating concept and how this can be used as a powerful tool in the scientific machine learning research itself. So let's get into the lecture. So don't worry, even if you are hearing about symbolic regression for the very first time, because we'll be starting with an extremely simple example. Let's say you have a data set which are input output pairs. So x comma y pairs, data set pairs. And let's say the relationship between x and y, although unknown to us, it was produced using this function, y equal to 2x square plus 3x plus 1. So the way to produce xy pair is you substitute some value of x. So let's say x equal to 1, corresponding y will be 2 plus 3 plus 1 equal to 6. Like that, you can produce xy pairs and you are just provided this xy pair. You are not told whether it was produced using a quadratic function or sinusoidal function or any other functional format. You have no information. Now, our goal is, provided the data set, can you uncover this particular underlying relationship? If yes, then it's very powerful. Why? Because this can be the relationship that governs some kind of physical phenomenon. Let's say you were Isaac Newton and you just had the data of position versus time of an apple falling. With just that data, could you uncover the Newtonian mechanics, or at least just the laws of gravitation? Is that possible? So this is a question that we are asking, and obviously we'll be trying to answer it with a very, very simple example so that for demonstration purposes, it's much easier. So what we have is, we have a XY dataset pair. So X values are 1, 5.75, 10.5, 15.25, and 20. And corresponding Y values are these. And when you plot the dataset on XY axis, it looks like this. So you might be tempted to say that there is a quadratic relationship, but you're not sure. It can be exponential, because you just have 5 data points and it's very hard to say what is the underlying relationship here, unless you do you perform some sophisticated calculations. So the goal is now, provided this data, is it possible for you to find out or backtrack the equation that produced this particular relationship between x and y? And once you backtrack that equation, will it look something like this, or will it be something else? Will it be cubic, or will it be exponential, or some other functional format? What would it look like? So this is the question that we are going to answer, and this technique comes under the category of symbolic regression. So we'll see what exactly is symbolic regression and how can we perform it on this particular data set. So in symbolic regression, we first start with data. But in today's lecture, we are also going to take a couple of assumptions. One is the function that governs the relationship between x and y. So if we write y equal to f of x, then we will assume that the format of this function is simple. It won't be like a cascade of a lot of functions. The reason why this assumption is valid is because in nature, any phenomenon when you take, if you truly understand the phenomenon, you can express that particular phenomenon as a balance between forces or factors that drive the phenomenon and forces or factors that oppose the phenomenon. If these two are in equilibrium, then you have a phenomenon that is stable. If there is an imbalance between either the driving factor and opposing factor, if one of them is larger, then you have a transient phenomenon. But at the end of the day, when you express this phenomenon in terms of partial differential equations or ordinary differential equations, the relationship or this expression will be generally a simple expression, which you will be able to express in terms of maybe a certain set of polynomials. So alpha x plus beta x square plus something. Sometimes there would be trigonometric functions, sinusoids and cosines. Sometimes there will be logarithmic functions. Sometimes there will be exponential functions, maybe a raised to x instead of e raised to x. But at the end of the day, these are the collection of functions that can usually represent most physical phenomena. Of course, there are exceptions. But today, for the purpose of demonstration, we'll be assuming that the functional format is simple and we can represent the final target function as a combination of few simpler basis functions. And these basis functions will be defined in something called as a library of functions, which I will show you soon what exactly it means. So this library means we will say that I'm going to define a set of functions which will form part of my basis functions. So my library now for this demonstration purpose, it looks like a collection of 6 functions: 1, x, x square, x cube, sin x, and cos x. So what this means is my final target function, which I'm trying to predict, can only be a combination of these functions. Now you may have a natural question: how is this assumption valid? What if there is a logarithmic function? What if there is an exponential function? Am I not missing out? Of course, that is correct. I am missing out. So what I can do is I can add those functions also to the library. So generally a good practice is to collect all the most common basis functions into your library so that you can hopefully have that functional form also when you are finally predicting the actual functional format of your phenomenon. But for the initial demonstration, let's start with a library of just 6 functions and we will see how to use this library to make a prediction. So let us start with the data set. We have the input output data pair. So x equal to 1, 5.75, 10.5, 15.25 and 20, and you have the corresponding y data. So first let's convert this into vector format. So it will be a column vector and the dimension of this column vector will be 5 by 1 because you have 5 data points as input and 5 data points as the output. Now once we have the input output pairs, we can construct something called as design matrix or phi. So this capital Phi denotes something that involves both your input data as well as your basis functions. So in our case, we have 6 basis functions, phi1 up to phi6. So phi1 is equal to 1, phi2 is x, phi3 is x square, x cube, sin x, and cos x, right? And the idea is that if y equal to f of x is the format of our input output relationship, then it can be expressed as beta 1 times phi 1 plus beta 2 times phi 2 plus etc. up to beta 6 times phi 6. So here phi 1, phi 2, phi 3, phi 6 are, and this will be phi 1 of x, right? Of course, this will be a function of x. Phi 1 of x, phi 2 of x, etc. And beta 1, beta 2 up to beta 6 are certain coefficients. Now, the size of this design matrix will depend on your number of basis functions as well as your data set size. But basically, this basis function set can also be called as hypothesis space. Why? Because you are assuming that your final format of the function is a derivative of a collection or a subset of these functions combined using certain coefficients. So let's see how this design matrix phi will look like. So this is our input data x, 5 by 1 matrix or 5 by 1 vector, and our design matrix phi will have certain columns. First column will be corresponding to phi 1 of x, second column will be corresponding to phi 2 of x, phi 3 of x, phi 4 of x, phi 5 of x, and phi 6 of x. And what is the x value? X value will be these set of phi values. So phi 1 of 1, phi 1 of 5.75, phi 1 of 10.5, phi 1 of 15.25, etc. We can also substitute the exact values or exact functional format of these basis functions. So first column will be simply a collection of ones because it doesn't matter what your input value is, it's just 1. Second will be equal to x, meaning whatever is the input value, that itself will be the value of this column. Similarly, x square, x cube, sin x, and cos x. So you can already guess what the dimension of this matrix phi is going to be. You will have 5 rows because you have 5 data points, and you will have 6 columns because you have 6 basis functions. So the dimension of this is going to be 5 by 6. In general, the dimension will be m by n, where m is equal to the number of data points you have and n is equal to the number of basis functions you have in your function library. So that is the dimension of this matrix phi. Now the question is, what are we going to solve? We are going to solve this equation, phi times beta equal to y. You might obviously have a doubt what exactly is beta here and what is y here, and I will clarify that. So phi is our design matrix, the 5 by 6 dimension matrix as we discussed earlier. Y is the output data set corresponding to our input x vector. So this will also be a 5 by 1 vector. And beta matrix is the set of coefficients. So if I scroll above, here I mentioned that y equal to f of x will be a summation of phi 1 to phi 6, as if it's a linear combination using the coefficients beta, right? So this beta matrix will be a collection of the coefficients. But what is the dimension of this beta? Here, if you look at the multiplication, you are multiplying a 5 by 6 matrix with some random matrix beta to get a 5 by 1 matrix. And in the matrix multiplication, we know that if you are multiplying 5 by 6 with m by n matrix, if you are multiplying these two, and if the result is something like a 6 by 1 matrix, then you know that m has to match, or sorry, this is not 6 by 1, this is 5 by 1. Then m has to match 6, otherwise multiplication is not possible. And n should be whatever is this number. So this will be m by n will be basically 6 by 1. And indeed, there will be 6 coefficients because you have beta 1 to beta 6 as denoted by this equation. So the beta matrix will be a 6 by 1 matrix which can be denoted like this: beta 1, beta 2 up to beta 6. Now what we are solving is this equation where phi times beta equal to y. Phi is a 5 by 6 matrix, beta is 6 by 1, and this is 5 by 1. Now obviously the dimensions of beta and phi are dependent on beta is dependent on both data set size as well as the number of basis functions. Phi, this 5 by 6 is dependent on data set as well as number of basis functions. Beta is just dependent on the number of basis functions because each basis function will be associated with a coefficient. Now the question is, how exactly do you interpret this equation? Let's say beta 2 was equal to 0. What does that mean? What it means is this linear component is not part of the equation. That is what it means. Because as I mentioned, y equal to beta 1 phi 1 plus beta 2 phi 2 plus etc. up to beta 6 phi 6, right? This is what we want to construct. So if beta 2 is equal to 0, that means whatever is the functional format of phi 2, that is not coming into the picture. And what is phi 2? Phi 2 we know in our library of functions, phi 2 is equal to x. So what that means is in our final functional format, if beta 2 was 0, x won't be present. Maybe x squared may be present, constant may be present, sin x, cos x, all of those can be present, but x won't be present. Similarly, if the value of beta 5 was very big, that means the coefficient associated with the basis function associated with the fifth index, that will be present with great dominance. And what is the fifth guy? It is sin x. So if beta 5 is very big, it means sin x would be present in the final functional format. So that is the physical interpretation of this equation. And what we are trying to find is what is the value of each of these coefficients beta, so that you can decide which basis functions can be eliminated from your function library, or which basis function will not be present in your final functional format. So that is the interpretation. So if beta 5 is small number, sin x will not be present. If beta 2 is a large number, then this linear component x will be present. If the value of beta 2 is large, meaning the coefficient of x is a large number. So that is the interpretation of this above equation. Now there is a problem. You might have noticed this. The issue is that you have 6 unknowns. What are those unknowns? 6 values of beta, but you have only 5 equations. But that is just an artifact of the number of data points and then the size of your basis functions which you took, right? So we decided to take 6 basis functions and we had 5 data points. But this was arbitrary. You could have added 1 basis function less in our function library. You could have had 2 more functions, logarithmic function, inverse, like 1 by x function. Data points could have been 5. There could have been 50 data points. So these 2 numbers are arbitrary. But you also know what this means. If you have same number of unknowns and equations, then there is a potential that you can solve that system of equations, provided there are no linearly dependent equations. And if there are more number of unknowns and less number of equations, then there are potentially more number of solutions possible. Similarly, if you have more equations and less number of unknowns, then you have an over constrained problem. So all these These three cases are possible. You may have equal number of unknowns in equations. You may have more number of unknowns. You may have less number of unknowns. It purely depends on what is the size of your basis function library and what is the size of your data set. And you typically don't have too much control over this. You may have n number of data points. Maybe you have almost always more number of data points than the number of functions. So finding an actual proper solution for beta is very unlikely. It is very, very unlikely that you will come across a set of values for beta, which will fully satisfy your condition beta phi multiplied by beta equal to y. But what is possible is you can find approximate solution to beta, which will approximately satisfy phi times beta equal to some y cap, where you can try to make y cap as close to y as possible. So now this will be an approximation. So you will be able to say 5 times beta approximately equal to y. 5 times beta is exactly equal to y cap, but it's approximately equal to y. And whatever is the difference between your predicted y and actual y, you can use this difference to construct something like a mean squared error function. And your goal could be to minimize that mean squared error, which is exactly what most machine learning algorithms do, right? In gradient descent, you decide a loss function. The loss function may be mean squared error, depending on whether you are working on regression or classification. It could be cross entropy loss, and you are trying to minimize it. So that is also the idea here. So you had 5 data points, but a library which consists of 6 functions. So you have 6 coefficients to find, right? So this is the nature of the problem. You don't have an exact solution to the beta in most cases. So to solve for beta, we can do something called as least square regression. And the mathematical format of this can be represented as beta cap equal to argmin of phi times beta. This is a matrix multiplication minus y, the whole square, the magnitude of this squared. Now this looks like a complex expression, but what it is saying is very simple. What it is saying is try to find a beta where you are calculating phi multiplied by a beta and see how far away this is from the value of y, because you started by saying that you wanted to solve 5 times beta. This is not dot product, this is matrix multiplication. 5 times beta equal to y is what you wanted to do. But since we are taking some random values of beta initially, you will not be doing 5 times beta equal to y, but rather 5 times beta, phi multiplied by beta will be equal to some y cap. Now you are looking at how close is your y cap to y, such that if you were to take the magnitude of this or mean squared error considering all the points, can you minimize this number, or can you find the beta which will minimize this number? So that is what this expression is saying. So in the plain English, we are trying to find best set of weights for beta. So beta 1 to beta 6 in our particular case, such that when we combine our basis functions using beta, then we get as close to y as possible. So that is our objective. Now we can very easily implement all this in code. I have already coded this in Julia, but I will also walk you through the code. It's only very few lines. This much is the code length. So it's very straightforward, but let me show you what all I have done here in the code. So here what I have done is we define the input output pairs. So instead of directly defining the values of x and y, I use the functional format. So functional format is 1 plus 2x square plus 3x, right? So this is 2x square. So 2 dot x dot raised to 2 dot plus 3 dot multiplied by x dot plus 1. So this dot is added so that it will be performed element wise. And x is a set of numbers ranging from 1 to 20, and I'm picking 5 numbers in this range. So 1 will be part of the list, 20 will be part of the list, and in between there will be equispaced numbers, 3 more numbers. If I define this length to be 20, I'll have 20 values in the x and corresponding 20 values in y. So that's the reason why I have defined it like this. Now I define my basis functions, and as we discussed, we have 6 basis functions: constant, x, x square, x cube, sin x, cos x. And here we can add any number of basis functions, and that also I will show you how exactly we can do. And then we construct the design matrix phi such that the columns are corresponding to phi 1, phi 2, phi 3, etc. And each individual row corresponds to one data point. So you have 5 data points here, so the size will be 5 by 6. Then amazingly, to solve for beta such that this constraint argument argmin of 5 dot beta minus or 5 times beta minus y the whole square. To minimize this, finding the value of beta, this part is very easy to perform regression, like sparse regression. You have a function which can be denoted as phi slash y. So this will solve for beta. Now you might be wondering, aren't there different cases? A case where you have equal number of unknowns in equations, more number of unknowns than the number of equations, and some cases more number of equations than the number of unknowns. And this function, this expression will automatically take care of all those cases, whether you have m greater than n, meaning whether you have more number of, whether you have equal number of unknowns and equations, or whether you have more number of unknowns and equations or less number. In all those cases, beta equal to phi slash y will automatically take care of that. And there is one more thing which we can technically do, which is adding something called as lasso penalty or ridge penalty. But we are not doing that. So this penalty is something where you perform something called as regularization or ridge regression, where what you do is you define your error or loss equal to 1 by n sigma yi cap minus yi the whole square. So this is the mean squared error plus lambda times, maybe either you can do the square of weights or you can do the absolute value of weights. So one of them will have, so this will make sure that the weights are not too high and some of the weights are brought closer to zero. This will ensure that some weights are completely converted to zero. So this is like a way to eliminate some of the coefficients which may not be part of your functional format. And this will also ensure that the weights are not very high, because if weights are very high, your loss will be very high, because this extra penalty term will contribute significantly to your loss. So this is an inherent way to prevent your optimization from bringing very big weights. In our context, what is the weight? Weights are the set of beta I values. So if any value of beta is so high, then it's not a good thing. Then meaning you are trying to overfit your function y equal to f of x equal to sigma beta I phi I. You should not be performing this I equal to 1 to 6. If any value of beta is very high, that means you are trying to overfit to this function, right? So you should ensure that you have some sort of regularization here, either a ridge regularization or a lasso regularization. In our case, we are not implementing it for now, but we'll see what is the output that we get. So let's do one thing. Let me open terminal and then let me also open Jupyter Lab, because I'll be running my Julia code in Jupyter Lab. So Jupyter Lab. So I have the Jupyter Lab open here, and code I have copy pasted here from this code block. So let's first run. Let's create the data points and the basis functions. So we run this code block. We have 6 basis functions: 1, x square, x cube, sin x, cos x. Next, what we do is we solve for beta using this expression phi slash y. And then when we run this, we get the values for beta. These are the values for beta. And interestingly, you can see, first let me also plot it like in the format of beta times phi 1 plus beta 2 phi 2, etc. right? So now this is the expression. So solution without having our lasso penalty meaning this guy, lambda times modulus of w or modulus of beta. We don't have lasso penalty. Without that, we have this expression. Our solution is 1.4214 times 1 plus 2.45x plus 2.0728x square, like that. So this solution is now the approximation to our actual function. So actual function is y actual equal to 1 plus 3x plus 2x square. But the thing is, we have no idea, or this model has no idea what the actual function is, whether it is quadratic or cubic or linear, no idea. Model just have access to the data. But what the model is now predicting is the predicted function is 1.4214 plus 2.45x plus 2.0728x square. There is x cube term, there is sin x term and cos x term. So obviously you can see that the predicted function is completely different from the actual function. But yet, if we try to plot this, if we try to plot the original data with the fitted data, fitted meaning you substitute the values of x to this function, then you are getting a very, very good match. So this is surprising, right? Why do you think you have a match between the original data and this fit data? Although the fit function looks like completely different from your actual function. The reason is, if you look at the dominant terms, so sin x and cos x, these two terms can maximum go up to, the value of sin can be between -1 and 1. So you're multiplying it by minus 0.36. Similarly, cos x is also between -1 and 1. You're multiplying it by 0.68. But if you look at the values of y, the range of values of y, it's like close to 800 in its upper range. So, which means these two terms are not going to contribute that much to the error. X cube term may contribute because the cube of 20 is 8000, right? But it's getting multiplied by around 0.0023. So the value of x cube is also, the contribution of x cube is also kind of probably diminishing. But there is contribution coming from x and x square somewhat. So maybe the majority of the contribution is coming from this, and somehow the contribution due to x and x cube are getting cancelled off each other to have a decent fit between your model and the original data. But I don't think we should be happy right now, because the predicted function is not at all looking like the actual functional format. So what might be the reason? Maybe the reason is for the sparse regression that we are performing, there is not enough data available. So what we can do is, maybe we can increase the number of data points. So instead of 5 data points, let's increase this to 20 data points, and let's see what happens. So when I have 20 data points, when I solve, I get a new values of beta. And now let's see. See, now if you don't have, if you have 20 data points, you don't have the x cube term, the coefficient has become 0. Sin x coefficient is 0. Cosine x is also 0. The only three terms you have is x plus 3x, sorry, 1 plus 3x plus 2x square. Is that exactly same as our format, function format? It is exactly the same. So when we have more data points, we are able to exactly recover symbolically what the original function format was, and the fit between original data and the model is again very good. Now you may have a natural question, because we conveniently chose this basis which includes x square, x1, etc. What if x square, for example, was not part of this? What would happen? Do you think we will still be able to make a good fit? Because it seems like our symbolic regression process is completely dependent on our basis library, right? Basis function library. That is exactly correct. It depends on the basis function library, which is why it's a great thing to do, to figure out what exact library are you going to start with. And you should obviously not be starting with just 6 functions in your library. Maybe you have 20, 25 functions, but with an array of 20, 25 functions, you can cover a good set of trigonometric functions, logarithmic functions, inverse functions, polynomial functions, linear function, constant, whatever. So what we can do is, let's try to eliminate this x square and see what happens. So now I don't have x square in my function, and let's run the code once again. I have 20 data points, and here instead of 1 to 6, I have only 5 values to regress, right? So now I have this, and I'm trying to create the fit. You see, the fit is not that good, and the function format is -36 plus 20x plus a very small number multiplied by x cube. Sin x is there, cos x is there. So here 20 data points are there, and it seems like fit is good, but the actual function format that is being recovered is not very good. And the reason for that is, we have omitted the x square term, which is actually present in the original function. The original function has this 2x square term. So without an x square term, you can't approximate the original function. Now, what if we remove x cube also? Maybe the fit will become even worse, right? So ideally, if x cube also was not present, the loss has to be very high. And how do you know if the loss has become very high or not? And here we'll change it to 4, because now we have only 4 basis functions. So you will see the loss is very high. When you plot, the fit between your prediction and reality will be very bad. You see, the reality are these dotted points, and your fit is this curvy points. And now what is the function? You have a constant, you have linear function x, and you have a sinusoid and cosine. So it is as if you have a line, and on top of this line, you are kind of overlapping sine and cosine. So it will look probably something like this. And that you can see here. See, it's looking a bit wavy, as if there is a sine superimposed over a straight line, right? So, and the fit is not good. And that is because now you don't have x square, you also don't have x cube. So this is the idea behind using the correct set of basis functions. What if you had some other wrong basis function? So let me add x square and x cube back. Let me put this as 6 because you have 6 basis functions. But what if you had, let's say, logarithm of x? So you have log of x as the 6th or 7th function. And here you will change the number to be 7. And let's run this to see what the output is. You see the coefficient associated with log is also now, oh, I have one more function to add. X square is missing. Okay. So x square, and yeah, I think that's it. So now you see that still the log is not contributing anything. The coefficient is 0, and your fit is now very good. So what this means is, so long as your basis function includes all the probable functions that would be part of your phenomenon, then you can exactly know which ones are contributing to your data and which ones are not. And here, although we had added useless log, it is automatically getting eliminated because the coefficient associated with the log function is 0. So this is how symbolic regression becomes a very powerful approach for uncovering the actual functional format for any given phenomenon. And this is primarily used in scientific machine learning framework. So that can be the last part of the SciML framework, right? Closing the loop. So what do we usually do in SciML framework? We start with some phenomenon, maybe throwing a ball up, or a chemical reaction, or let's say nuclear plasma, or dynamics of growth or shrinkage of a black hole, whatever it is. The phenomenon will be governed by a set of ordinary differential equations or partial differential equations. Then you will have your data set, which are either produced out of real physical experiments done based on the phenomenon, or your data set is simulated data set on top of which you add Gaussian noise. Then what you do is you try to construct a scientific machine learning framework where first you split your data set into training, and then remaining will be for validation or forecasting. And you either train a neural ODE framework or UDE framework, the details of which is not relevant for the purpose of this lecture. But basically, these are two major frameworks used in SciML, in scientific machine learning. And what is being shown here is, even if you use 20% of data for training and 80% for forecasting, you can sometimes show that UDE framework still works. Even in the absence of 80% of the data, forecasting is still very good. That we have showed in several projects using UDE. So you can show that you have a scientific machine learning framework. If you have no knowledge about the system, you use neural ODE. If you have partial knowledge about the system, you use UDE. And you show that you can train this SciML framework on your data set so that you can have good training accuracy and you can have good forecasting or good validation. Then based on this good framework, you try to make predictions on new input data points, right? And the goal is now, this much is enough for many scientific machine learning papers. They stop at this stage, saying that now they have a new SciML framework in their particular domain, whether it's cancer biology, whether it is physics, astrophysics, or finance, economics, whatever it is. They say that, hey, we have created a new SciML framework which can make predictions even in the absence of significant amount of data. Then this is where many SciML papers are concluded. But there is a beautiful way in which you can close the loop. And the loop is symbolic regression that we discussed today. On the data that you make predictions of, you perform symbolic regression and show that if you know the functional format of your original phenomenon, which is the case in many phenomena of well-studied nature, you show that using your symbolic regression on top of the data set that you predicted using neural ODE or UDE, you are able to recover the original functional format. If you can do that, it beautifully closes the loop of the SciML research framework. And if you can, although I explained this in like 3 or 4 or 5 sentences, so it may look like it's a simple thing, but if you can implement this in your particular domain on an impactful problem statement, and if you can write this scientific story in the format of a paper, it can go into really good conferences, because this is not something that is that easy to do, and this is not something that is widely being done in different fields, because SciML is an upcoming field. But I hope you really understand and appreciate the importance of symbolic regression. I'm fully aware that the example that I took today for demonstration purpose is too simple. I could have picked a bit more complex example, but then the code would have been longer and it would have taken me a longer video to explain all of this. But I hope you understand the point and significance of this symbolic regression or sparse regression. So with that, we can wrap up today's lecture. Thank you so much for listening. We'll meet again in another lecture. Take care until then. Bye.